We will start with the problems on torsion of circular shafts in this video. So the first problem, a solid stepped bar of circular cross section shown in figure is subjected to torque of 1 kilonewton meter at its free end and a torque of 3 kilonewton meter at its change in cross section. Determine the angle of twist and shear stress in the bar. Take E is equal to 2 into 10 to the power of 5 Newton per mm square and G is equal to 7 into 10 to the power of 4 Newton per mm square. So we can see the figure here. So this is a solid stepped bar of circular cross section. Two different cross sections are there. One is of 100 mm and the other one is of 50 mm diameter. The 100 mm diameter is of 200 mm length and 50 mm diameter is of 400 mm length. So at the portion of change in cross section, that is at this point, it is subjected to a torque of 3 kilonewton meter as told in the problem at this point. And at this point, it is subject to a torque of 1 kilonewton meter. You can see here. Okay. Now we have to determine the angle of twist and shear stress in the bar. Okay. So first we have to write down the FE model. Okay, basically this is of two elements problem with three nodes, node 1, node number 2 and node number 3. So at change in cross section we are placing one node, initial node and a final node. Two elements, element 1 and element 2. Element 1 is of 200 mm length, element 2 is of 400 mm length. T1 theta 1, T2 theta 2 and T3 theta 3 at node number 1, 2 and 3 respectively. So the equation for J is pi into d to the power of 4 by 32. This is used for calculating the stiffness matrix. So in our previous derivation we have derived the equation for stiffness matrix of our bar which is subject to torsion, that is Gj by L 1 minus 1 minus 1 1. So since there are two elements, we are taking two stiffness matrix. The first one is K1, G1 J1 by L1 1 minus 1 minus 1 and 1. The value of G was given, that is 7 into 10 to the power of 4. J is 9.82 into 10 to the power of 6. And we have to do necessary unit conversions wherever it is required. Divide by length 200 mm. 1 minus 1 minus 1 1. Upon simplification we will be getting it as 10 to the power of 9 3.44 minus 3.44 minus 3.44 and 3.44. This is for element 1. Now for element 2 stiffness matrix, K2 is equal to G2 J2 by L2 1 minus 1 minus 1 and 1. G is same for both the elements. G is 7 into 10 to the power of 4 into J is pi into 10 to the power of 4 by 32 as it was told previously. J2 is different. Upon solving for J2, we will be getting it as 613.59 into 10 to the power of 3 divided by length Length of element 2 is 400 mm. Word 1 minus 1 minus 1 and 1. 10 to the power of 9, 0.107 minus 0.107 minus 0.107 and 0.107. So this is for stiffness matrix K1 and this is element of stiffness matrix K2. Now the global stiffness matrix, that is sum of the stiffness matrix K1 and K2. Upon adding both this stiffness matrix, we will be getting this matrix, that is K is equal to 10 to the power of 9, 3.44 minus 3.44, 0, minus 3.44, 3.547, minus 0.107, 0, minus 0.107 and 0.107. So this is by adding both the elemental stiffness matrix, we will be getting this. Okay. So a simple addition method is, these are the values for element 1, these are the values of element 2. Element 1 means node 1 and 2. So at this point we will be writing 1 2 1 2, and at this point we will be writing 2 3 2 3. So for element 2 the nodes are 2 and 2 3 2 3. Okay. So for this entire matrix there are 3 elements, sorry 3 nodes, node 1, node 2, node 3, 2 elements, node 1, node 2, node 3, node 1, node 2, node 3. So upon writing 1 2 3 1 2 3 horizontally and vertically, we will be substituting those values here, and we will be, wherever it is required, we will be adding it and we will be writing the value. Simple method of addition. So this is how we get the global stiffness matrix. Next, we will be finding the load vector. We have to find the load vector. T is equal to T1, T2, T3. That is a torque at node number 1, 2 and 3 respectively. This means T means transpose. This T means transpose. We have written in horizontal form instead of writing in vertical form. So it is written as transpose here. T is equal to T1 is 0, T2 is 3, T3 is 1. We have substituted the values. T is equal to 0, 3, 1 and transpose. This means transpose. If we write it in vertical means there is no need to write this transpose. So the equilibrium equation for the torsion of shaft is K into theta is equal to T. K into theta is equal to T. K is a stiffness matrix, that value we have got. Theta we have to write down. So how many angle of twist are there? 3 are there. Those are theta 1, theta 2 and theta 3. T, that is the torque. 3 torques are there, 0, 3 and 1. So in the given problem, the boundary condition is the first end is fixed. Okay. So theta 1 is 0. So by using the elimination approach, what we do is we eliminate this first row and first column. We use the first row and first column, eliminate it. So this we eliminate this first row and first column. So upon eliminating it, we will be having, by applying the elimination method, the remaining will be 10 to the power of 9, 3.547, 3.547 minus 0.107 minus 0.107, 0.107, theta 2, theta 3, so and 1. Those were the angle of twist. So upon solving this, now to find the shear stress, theta 2 is equal to 1.162 is equal to G into n radians. and theta 3 is equal to, so we know that T by J is equal to tau by 0.050 into 10 to the power of minus 8. So tau is equal to what? GR by L into theta 1 minus theta. This is how we get it. Similarly, T1 is equal to what? GJ by L into theta 1 minus theta 2. So this is for the general result. So for element 1, tau 1 is equal to G value we know 70 to the power of 4. Radius is 50 divided by 200 into theta 1 is 0. So theta 2 is 1.162 into 10 to the power of minus 9. So further simplification, upon further solving, we will be getting the value of tau 1 as 2.03 into 10 to the power of minus 5 Newton per mm square or 20.3 Newton per meter square. Similarly, for element 2, tau 2 is equal to G2 R2 by L2, theta 2 minus theta 1. G2 is 700 to the power of 4 into 25 divided by 400 into 1.162 into 10 to the power of minus 9 minus 1.050 into 10 to the power of minus 8. So tau 2 is equal to 4.085 into 10 to the power of minus 5 Newton per mm square is equal to 40.85 Newton per meter square. So this is how we determine the angle of twist theta and the shear stress tau for the problem given. So we'll go for the second problem. A bar of circular cross section having a diameter of 50 mm. So this is a uniform cross section bar. It is firmly fixed at its ends. Both ends are fixed and subject to a torque B and C as shown in figure. Determine the maximum angle of twist and shear stress. Take G is equal to 7 into 10 to the power of 4 Newton per mm square and E is equal to 2 into 10 to the power of 5 Newton per mm square. E is equal to 2 into the power of 5 Newton per mm square. So this is a uniform cross sectional bar. You can see at different lengths are given at different points, 4 points A, B, C and D, and at point B it is subjected to 1 kilonewton meter and at point it is subjected to 1.5 kilonewton meter. Okay, the polar moment of inertia J is 0.2 to the power of 4 by 32. It is same for the entire problem because it is of uniform cross section. Pi into 50 to the power of 4 by 32 is 6.135 into 10 to the power of 5. So this is the FE model of the problem. 3 elements, element 1, element 2, element 3 with 4 nodes, node 1, node 2, node 3 and node 4. T1 theta 1, T2 theta 2, T3 theta 3 and T4 theta 4 for element 1, element 2, element 3 and element 4 respectively. So the stiffness matrix for element 1 is K1 is equal to Gj by L 1 minus 1 minus 1 1. Substituting the values 7 into 10 to the power of 4 into 6.135 into 10 to the power of 5 divided by 2000. Necessary unit conversions have to be made wherever necessary. 1 minus 1 minus 1 and 1. 10 to the power of 6, 21.5 minus 21.5 minus 21.5 and 21.5. Stiffness matrix for element 2 is K2 is equal to Gj by L 1 minus 1 minus 1 and 1. 7 10 to the power of 4 into 6.135 10 to the power of 5 divided by 1000. 1 minus 1 minus 1 and 1. 10 power 6 42.9 minus 42.9 minus 42.9 and 42.9. Similarly, the stiffness matrix for element 3 is K3 is equal to K to the power of 6 42.9 minus 42.9 minus 42.9 and 42.9 because the length is also same. So 3 elements with 4 nodes. For element 1, node number 1 and 2, 1 2 1 2. For element 2, 2 3 2 3. For element 3, 3 4 3 4. The global stiffness matrix 4 nodes, node 1, node 2, node 3, node 4, 1 2 3 4 horizontally and vertically 1 2 3 4. So upon adding, we will be getting this global stiffness matrix, that is K is equal to 10 to the power of 6, 21.5 minus 21.5, 0, 0, minus 21.5, 64.4, minus 42.9, 0, 0, minus 42.9, 85.8, minus 42.9, 0, 0, minus 42.9, and minus 42.9. So this is the global stiffness matrix. So next, the load vector T is equal to T1, T2, T3, T3, and T4. 4 nodes. Transpose. I am letting this horizontal. T is equal to T1 is 0, T2 is 1, T3 is 1.5, and T4 is 0. The equilibrium equation is K into theta is equal to T. Stiffness matrix K, theta, theta 1, theta 2, theta 3, and theta 4. T, I am writing vertically 0, 1, 1.5, and 0. So the boundary condition is first end and the last end is fixed. So theta 1 and theta 4 both are 0. Theta 1 is equal to theta 4 is equal to 0. So by elimination method, what we do is we eliminate the first row, first column, and we eliminate the last row and last column. By eliminating all those, the remaining terms is 10 to the power of 6, 64.4, minus 42.9, minus 42.9, and 85.8. Theta 2, theta 3, that is equal to 1 and 1.5. So upon further solving this, we will be getting the value of theta 2 as 4.074 into 10 to the power of minus 8 radians, and theta 3 is equal to 3.785 into 10 to the power of minus 8 radians. Next, we have to find the elemental stresses. For element 1, shear stress Rho1 is equal to G R1 by L1, 1 minus 1 minus 1 1 into theta 1 theta 2, because theta 1 and theta 2 are the angle of twist of element 1 at node number 1 and 2. So theta 1 theta 2. 7 into 10 to the power of 4 into R1 is 25 divided by 2000, 0 plus 4.074 into the power of minus 8. For the simplification, we will be getting the value of tau 1 as 3.564 into the power of minus 5 Newton per mm square, 35.64 Newton per meter square. For element 2, shear stress, tau 2 is equal to G into R2 by L2 minus 1, 1, theta 2, theta 3. 7 into 10 to the power of 4 into 25 divided by 1000, minus 4.074 into the power of minus 8 plus 3.785 into the power of minus 8. By solving, we are getting a value of tau 2 as minus 5.057 into 10 to the power of minus 6 Newton per mm square. That is minus 5.057 Newton per meter square. Theta 2 and theta 3 for element 2, because the nodes of element 2 are node number 2 and node number 3. Next, for element 3, shear stress tau 3 is equal to G R3 by L3 minus 1 1 theta 3 and theta, because for element 3 the nodes are last two nodes, that is node number 3 and node number 4. So those angle of twist theta 3 and theta 4. 7 into 10 to the power of 4 into 25 divided by 1000 into minus 3.785 into 10 to the power of minus 8 plus 0. For the simplification, we will be getting the value of tau 3 as minus 6.623 into 10 to the power of 5 Newton per mm square, or minus 66.23 Newton per meter square. So this is how we find the angle of twist and the shear stress for the bar which is subjected to a torsion. In this problem, we solved for 3 elements, and in our previous problem we had solved for 2 element